Hello, and welcome back to another speedrun, IB Math Speedrun with me, Vince. And today we're going to be going through Unit 3.2, which covers complex numbers. So let's jump right in. So, this is where it gets funky. If you've never heard of a complex number before, consider the square root of -1. What is it? The thing is, you can't express this in terms of any real numbers. It's not equal to 1, it's not equal to 2, it's not equal to -1. You can't do it. And so that's where complex numbers come in. Complex numbers allow us to express the square roots of negative numbers. That's at its heart. So we label -1 as equal to I. Because we define I squared as equal to -1. So yeah. An actual complex number takes the form of, we usually use the letter Z is equal to A plus BI, where A and B are real numbers. And so A is called the real part of Z, and B is called the imaginary part, since B is the one being multiplied to the imaginary number. So we need to also look at complex numbers geometrically, and I think we'll get a bit into this more later. But if you imagine, we have originally we only have the real number line here. It's like 0, 1, 2, 3, -1. But to express complex numbers, we need to add another axis to this line. We need to draw a vertical axis representing all of the complex numbers. So this would be all of the real numbers, and this would be all of the complex numbers. And so we can graph any complex number on this plane, just as we can write any real number on the number line. And so this complex number would be at a distance, A, B, sorry, these axes should actually be real and imaginary. And so this complex number would be A plus BI. And we can get a lot more into this later. But the one other thing we need to know is we need to know the modulus. So the modulus of a real number is, of course, its itself when it's greater than 0, and it's negative of itself when it's less than 0. Right? But what is the absolute value of, or modulus of, a complex number? And well, we define it as the square root of, we define it as really the magnitude of the number, if you think of this in a geometric sense. So the absolute value of a complex number would be the distance from the origin to it, just as the absolute value of a real number is equal to the distance from it to the origin as well. So this would be equal to the square root of the real part, so A squared plus B squared plus the imaginary part squared, all square root. So the modulus of complex number is always a positive real number, just like the modulus of a real number is always a positive real number aside from 0. So now we need to talk about some operations with complex numbers. So say we have two complex numbers, Z1 is equal to A plus BI, and Z2 is equal to C plus DI. Well, what if we want to add Z1 plus Z2? If we want to add these numbers, then we simply add their real parts and their imaginary parts. So this would be equal to A plus C as the real part, and then B plus D, I, as the imaginary part. Yeah. So next, we need to go through multiplying complex numbers. So say we are multiplying a complex number by lambda. So this is a real number, and we want to multiply it to a complex number. Well, the new number would be equal to lambda A plus lambda BI. We multiply the real number to each of the real and imaginary parts separately. And so finally, what if we want to check if two complex numbers are equal? Well, two complex numbers are equal and only equal if both the real and imaginary parts are equal. So in this case, we have two complex numbers, and they are only equal if A equals C and B equals D. If A equals C but B doesn't equal D, they're not equal. If B equals D but A does not equal C, they're also not equal. So yeah, that is it. So now we can jump into some problems involving complex numbers. I'll be doing the even ones because, you know, they're harder. So the first problem we have is we need to find the let me type this out. We need to find the real and imaginary parts of the following numbers. And the first number we have is z is equal to 5. And the thing is, all real numbers are actually imaginary numbers, except that the imaginary part is just set to 0. So we can actually think of this number 5 as 5 plus 0i. So the real part is clearly 5, when we denote the real part as rez, and the imaginary part, which we denote as im, is equal to 0. So yeah, that was it. And let's move on to the next one. So the next one is z is equal to 5 minus 12i over 13. So, well, what's the real part? The real part would be equal to 5 over 13, since that's the real part of this number. And the imaginary part would be equal to negative 12 over 13i, technically. And so this is because we can split this into 5 over 13 minus 12 over 13i. So yeah, that was pretty simple. So now, the next problem is given the complex numbers, z1 is equal to 3 minus 4i. Actually, no, sorry, no, I skipped a problem. We need to find the modulus of each of the complex numbers that were in part 1. So if we remember z5, well, what's the modulus of z? The modulus of z would be equal to, well, there's no imaginary part, so it would simply be the modulus of a real number, 5. But how about the next one? That one was a bit more interesting. So we have z is equal to 5 minus 12i over 13. Well, what's the modulus of z? The modulus of z would be equal to the square root of the real part, which is 5 over 13 squared, plus the square root of the imaginary part, which would be 12 over 13 squared. And so this would be equal to the square root of 25 plus 144 over 169. And actually, you'll find that this is equal to 1. So we have the square root of 1, which is equal to 1, since 25 plus 144 is equal to 169. So the modulus would be 1. Okay. Now, on to the final few problems. So we're given the complex numbers zi is equal to 3 minus 4i. Sorry, z1, and z2 is equal to 5 plus I. And z3 is equal to negative 1 plus 2i. We need to calculate the following and check your answers with a calculator. So, the first thing we need to calculate is 2z1 plus 3z2 minus 4z3. Well, 2z1 is going to be equal to 2 times 3 minus 4i. Plus 3z2, which is 3 times 5 plus I, plus 4z3, which is 4 times 1 minus 2i. Oh, sorry, minus 4z3, which is minus 4 times 1 minus 2i. So first, let's say negative 1 plus 2i. Oops. So let's first multiply to each term. So we have 6 minus 8i plus 15 plus 3i minus, plus 4 minus 8i. So if we add all the real terms together, 6, 15, and 4, we get 25. And if we add all the imaginary terms together, we get negative minus 13i. So our final number would be 25 minus 13i. Okay. Now we're going to the next one, and that we need to solve 4z1 minus 5z2 plus 2z3 over 3. So this would be equal to 4 times 3 minus 4i plus 5 times 5 plus I. Sorry, minus 5 plus 2 times negative 1 plus 2i, all over 3. So again, let's expand the terms. So this would be 12 minus 16i minus 25 minus 5i minus 2 plus 4i over 3. So that would be equal to 12 minus 25 minus 2, real parts first. So that would be equal to 12 minus 27, which is equal to 15. Negative 15. Negative 16i minus 5i plus 4i, well, that would be negative 21 plus 4i, which is equal to negative 17i. So we have negative 15 minus negative 17i over 3, and I think it should be fine to leave it like that. Oh, sorry. I realized my mistake. It's because they wrote the tiny numbers in such a small font that I read them wrong. So let me just rewrite the entire question. It's actually supposed to be, we have 4z3 minus 5z1 plus 2z2 all over 3. And so this would be equal to 4 times negative 1 plus 2i minus 5 times 3 minus 4i plus 2 times 5 plus I. Okay, all over 3. So this would be equal to negative 4 plus 8i minus 15 plus 20i plus 10 plus I, all over 3. Oh, sorry, plus 2i. Yep. And so we should have real parts first. So negative 4 minus 15 plus 10 is negative 4 minus 5 is negative 9, and plus the imaginary part, which is 30i over 3. So this is simply equal to negative 3 plus 10i. Yeah, so that was all for this speedrun. I hope you enjoyed, and I hope you now know a bit more about complex numbers than you did before, and I hope to catch you in the next speedrun. See you then.